Okay, we're going to continue chapter 8 worksheet. So on number 6 it says draw the Lewis structures for each of the following molecules or ions which do not obey the octet rule. So the first one is NO. So this one, nitrogen has 5 electrons, oxygen has 6, so we have 11. So right away we already know this is not going to obey the octet rule because we have an odd number of electrons. So go ahead and draw this. We have 2 electrons we've already used, and then 4, 6, 8, and then 10 and 11. Okay. So we can attempt to get everybody as close to an octet as we can. So oxygen has an octet, 2, 4, 6, 8, and nitrogen has 2, 4, and 5 electrons. But if we remove these and share them, then we do get to 2, 4, 6, 7 electrons on nitrogen. So it doesn't obey the octet rule. Like I said, you can already tell that at the very beginning when you have an odd number of electrons. Okay, so that was A. B, we have BF3. So B is going to be in the middle, F around it. And so boron has 3 valence electrons. Fluorine has 7, and there's 3 of them. So we get a total of 24 valence electrons. So I put my lone pairs on the outside atoms. Okay, and that's all 24 electrons. So the fluorines have an octet, but boron doesn't. And so normally at this point we would say, okay, we need to share some electrons to get boron to an octet. But remember, boron is that tricky one that can have less than an octet. So we would not put a double bond here. So this one does not obey the octet rule. But that's okay because it can have less. Okay, then we have C, is ICl2 negative. Okay, so this one, I is going to be in the middle, and then we need our valence. So we have 2 chlorine, which is 7, right? They have 7, and then we have another 7 with iodine, and then we have a +1 with that negative charge. So we have 22 electrons. Okay. So we can start by putting our lone pairs around the outside chlorines. Okay, and we've used 16, so I've got a lot more to go here. So anytime I have anything left over, it always goes on the central atom. So I've used 16, but I have 6 more to go. So we can do that by putting them as lone pairs on the central atom. So it looks a little weird because we have 3 lone pairs on the central atom, but that is the correct way to do that. Okay, so this does not obey the octet rule, right? Because we've overloaded the I, which is an exception that we can do, but it does not obey the octet rule. Okay, D is a little tricky, okay? So on this one, we have OPBr3. So P is going to be in the middle because it's the least electronegative. O, and then the bromines around it. Right? So oxygen. Okay, oxygen has 6. And then phosphorus has 5, and then bromine has 7. Right, so 6, 5, right. So we get 32 electrons. Okay, we're going to put the lone pairs around the outside atoms. Okay, so that is all 32 electrons. Everybody has an octet. So at this point we could say, yes, it does obey the octet. If we were to do formal charge, then we would draw it like this. Okay, but it didn't ask us to draw based on formal charge. But if we were, then this one would not obey the octet rule. Okay, so does not obey. So that one's a little tricky. I'm not gonna give you anything like that where it could go either way. So that first one does obey the octet rule. Okay, and the last one, XeF4. Okay, so we're gonna put xenon in the middle. And then the fluorines around the outside. So xenon has 8, fluorines have 7, and there's 4 of them. So we get 36. That doesn't seem right. Oh yeah, that's right, okay. Questioning my math here. Okay. Okay, so we've used 32 electrons here. We've got 4 more to go. And again, anytime I have any left over, they always go as lone pairs on the central atom. Okay, so xenon has more than a, excuse me, an octet, so it does not obey the octet rule. So the only one that did was this one right here, was D. Okay, let's do number 7. Okay, this one says, which is the most electronegative atom in the following sets? Okay, so we have sodium, magnesium, potassium, and calcium. So let me grab. So on the test, well, let's just do it this way. On the test, I'm going to give you the electronegativity table. So you could just even look these up if I gave a question like this. So magnesium would have the highest electronegative, or the most electronegative atom out of these. I'm trying to find a periodic table here. Oh. Let's see here. Okay, so we had, what was it? Sodium, magnesium, potassium, and calcium. So remember, the higher to the left, no, I'm sorry, to the right and up, you know, fluorine has the highest electronegativity, so it increases going across the period and it decreases coming down. So since magnesium is to the right corner, to the, you know, top right, then it would have or it would be the most electronegative, sorry. I think what I'm saying here. Okay, B, we have phosphorus, sulfur. Okay, let's see here. Phosphorus is right here, sulfur, arsenic, and selenium, same thing. So we would pick sulfur because it's the top right one. Okay, so B, sulfur. C, we have beryllium. Make sure this is in there. Beryllium, boron, carbon, and then silicon. So that one kind of dropped down, but it would be carbon, top right again. Okay, E, we have zinc, germanium, gallium, and arsenic. So it'd be arsenic, right? Because it increases going across the period. Okay, so C was C. And then D was arsenic. Okay, number 8 says, based on the loose structures, predict the ordering of NO bond links in the following ions. So we have NO, okay, so NO plus. So in this one, we would have 5, 6, for our valence, and then -1 because we have a plus, so we have overall 10 valence electrons. Okay, so we're gonna put 2, 2, 4, 6, 8, and 10. Okay, but we've got to share some electrons because neither one of them have an octet. So I hope this pen, marking it out doesn't confuse you. I just thought the pen would show up better in the video. So I'm moving those lone pairs over here to double bond. So that gives nitrogen an octet, but oxygen still only has 6. So I'm going to share these electrons now to get a triple bond. And so now both of them have an octet. And don't forget, if it is an ion, you need to put your brackets with the charge. Okay, then we have NO2 negative. So this one we would have 5 for nitrogen. Oxygen has 6, and there's 2 of them. And then we have a negative, so we're going to add 1, so we get 18. Okay, so we have nitrogen in the middle, oxygens. We can start by putting our lone pairs. So that's 16 electrons. Okay, so we have 2 left over. It goes on the central atom. Okay, so the oxygens both have an octet, but nitrogen doesn't. So I'm going to take one of these and share it, and it doesn't matter which oxygen we did that with. So remember, that always shows us we have resonance. So we don't need to draw the resonance structures for this, but just a reminder. Okay, so we're done with that one. And then last of all, we have NO3 negative. So we're going to have 5, and then oxygen we have 6 times 3 plus 1 gives us 24. Okay, so we're going to put nitrogen in the middle, and then we can add our lone pairs around the oxygens on the outside. Okay, so that's all 24 valence electrons, but we do have to get to an octet, so we're going to share one of them. It doesn't matter which oxygen, so again, that shows us we have resonance structures. So I'm going to take this lone pair and share. Now that gives nitrogen an octet. Okay, we can put our brackets with our charge. Okay, so there's the Lewis structure for all 3, and it says predict the ordering of NO bond links. So remember, triple bonds are the shortest, right? So NO plus has a triple bond, so it's going to be the shortest. Okay. Then we have a double bond for NO2 negative and a double bond for NO3 negative. But this double bond is only shared between 2 oxygens. This double bond is shared between 3 oxygens. So the bonds aren't going to be pulled in as tight for this one as they would be for this one because they're more spread out. So this ion or this bond length is going to be shorter than these. Okay, so if I have to share that double bond across 3 different atoms, it's not going to be as tight. It's not going to be pulled in. So NO2 negative would be our next one, and then the longest bond length would go to NO3 negative. Okay, number 9 says arrange the bond in each of the following sets in order of increasing polarity. Make sure we can, okay. So they're all paired with fluorine. So if we look at a periodic table here, and get that in there. Okay, fluorine, remember, has the highest electronegativity. And then we have oxygen, carbon, and beryllium. So electronegativity increases going across the period, and we're supposed to put them in order of increasing polarity. Okay, so the most polar bond is going to be between beryllium and fluorine because beryllium has a lower electronegativity number, so it's going to have the highest polarity because the electronegativity difference is going to be the greatest, and then carbon, and then oxygen. So it'll look like this. OF is going to have the lowest polarity, and then CF, and then BEF. And so the greatest difference in electronegativity is going to have the highest polarity. Okay, and then the next one, just bring this back in here. Okay, the next one, we're kind of all over the place. Okay, so SBR, CP, OCL, so I have these numbers right in front of me. Let me grab them real quick. Okay. So we have OCL. So those are really close to each other. So they're both going to have high electronegativities that are going to subtract out. So CL is 3 and O is 3.5. So we're going to have a difference of 0.5. Let's see here. What did I say? OCL. So the electronegativity difference is going to be 0.5. So it's polar, but it's not very polar. Okay. And then we have SBR. Okay, so bromine is 2.8 and S is 2.5. So we have a difference of 0.3. So that bond is nonpolar. And then CP. Okay, so C is 2.5 and phosphorus is 2.1. So we have a difference of 0.4. So these two bonds are actually nonpolar. So this one, SBR, would be the smallest or least polar, because it's not polar at all. And then CP, and then OCL. Okay. C, we have CS, and those actually have the exact same electronegativity. So its electronegativity difference would be 0. They're both 2.5. BF, so fluorine has 4. Oops. And then boron has 2, so we'd get a difference of 2. And then NO, so nitrogen is 3, oxygen is 3.5, so our difference would be 0.5. So the most polar bond would be this one right here. Has a greater difference there. So it would start with CS, that would be the least, and then NO, and then BF. Okay, let's go to number 10. It says calculate the formal charge on the indicated atom in each of the following molecules or ions. So the first one we're going to do is the central oxygen and ozone, O3. Okay, so when we draw the Lewis dot structure, I'm just going to draw what it looks like. Sorry, I've got it too close to my 10 right there. So it looks like this, okay? So when we do the formal charge, we take the valence minus assigned. Remember, we're going to count 1 for each bond and then each electron in the lone pair. So 1, 2, 3, 4, 5. So we get a positive 1. Okay, and then, let's see here. Then we have B. This is PF6 negative. And I actually wrote the wrong answer in the answer sheet. I'm sorry about that. I drew it wrong for some reason. And so I'll give you the correct answer here. So we have fluorine. There's 6 of them, and each have 7 electrons, valence electrons. And then phosphorus has 5, and then we have a negative 1. So it's a total of 48 electrons. So we've got P in the middle, and then we're gonna have 6 fluorines around the P. Okay, and then when we put our lone pairs in, Okay, so we have used all 48 electrons. So phosphorus valence is 5, and we've got 1, 2, 3, 4, 5, 6. So it'd actually be a -1. So I think I accidentally put a 0 in your answer sheet, but it should be a -1. So again, sorry about that. Okay, then C, we have nitrogen and NO2. So it's NO, and this one has an odd number. Okay, so we're gonna take 5, our valence for nitrogen, and then 1, 2, 3, 4. So we're gonna have an overall +1. Okay, D was iodine and ICl3. Okay, which looks like this. We're gonna have 2 lone pairs on iodine. So iodine has 7 valence, and then we have 1, 2, 3, 4, 5, 6, 7 assigned electrons. So our formal charge is 0 on iodine. Okay, then E, here's the last one. Chlorine and HClO4. Okay, so this one we're gonna have chlorine is in the middle, and then the oxygens around it, and then hydrogen's gonna be attached to one of the oxygens. We'll put our lone pairs in. Okay, so chlorine has 7 valence, and we only have 1, 2, 3, 4 assigned. So we're gonna get a +3 on chlorine for our formal charge. Okay, let's do number 11. Okay, number 11 says, draw the best Lewis structure based on formal charge of N2O. Okay, so N2O, N is going to be in the middle because it's not as electronegative as oxygen. And so we're going to have 16 electrons that we need to use. So we're going to do all the valence on the outside here. So we're going to have to share electrons to get everybody to an octet. So the central atom only has 4 electrons. So we can share here. And now it has 6, and then we can share again here. Okay? But we could also do where we just share from the nitrogen and get a triple bond. Okay, so those are the 2 possible structures. Those are the 2 possible structures that we can have. So doing the formal charge, we have 5, 5, and 6 for valence, and the assigned is 1, 2, 3, 4, 5, 6. And over here, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. So we're going to get a -1, +1, 0 for our first structure. Okay, on the second structure, we'll do the same thing, valence, and then assigned is 1, 2, 3, 4, 5, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7. So we get the negative now on oxygen. So anytime we're trying to choose the best structure like this, we want the negative charges to be with the more electronegative atom. So oxygen is the more electronegative atom here, so we want the negative to be on it and not the nitrogen. So this one right here would be the best structure.